Okay, well, my name is Anil Kulkarni. I am at Pennsylvania State University, Mechanical Engineering. I've been a professor there for more than 35 years. Just to give you a little bit of background, I graduated from IIT Bombay with 2 BTechs and did my PhD at Brownian University, and then since then I'm at Penn State. So I'm going to talk about mathematical modeling of a certain manufacturing technique called electron beam physical vapor deposition. And the reason I chose to talk about this, I mean I kind of have a workshop about this, was because number one, it's a very we just finished this work earlier this month, in fact, first week of this month. My student Kevin, he actually put together a presentation, many slides, but that is the project that we had. It has been going on for a while. Takes good 5 or 6 years of full-time work. And the way typically it works is that we have a research project, we come up with a certain title and thesis, thesis project scope, and then the student comes and joins and does the project. So 2 of us were working on that. I'm from mechanical engineering side and Dr. Singh is from materials side. This is a interdisciplinary project between mechanical engineering and material science. And so I wanted to show you how these interdisciplinary projects work. And the other thing I wanted to show you is that how we can take a practical problem and it can become very fundamental research problem. And it can get very involved mathematical problem. So modeling of electron beam physical vapor deposition. So I'm going to talk about coating. Okay, there is coating in many places that we see. Do you know of any examples of coating? Any type of coating. Why do we do coating and where is it? Paint, that's a good example. Exactly, investment casting. Electroplating, that's very, I mean, including, your 1 gram gold jewelry and all that, there's this coating there. And coating is very important. So painting, what you just said, it's there. And what it involves is basically we have a substrate of whatever shape, or you can think of as a car handle or something. It looks nice and shiny, but inside that it is not that. It basically is a coating that is showing. And there are different types of coats that you put on there for different purposes. Usually it is to protect the part, but also so that it becomes stronger or it looks prettier, or all those different things. So these are very typical examples. But when you go in engineering, there can be very advanced level. Well, this is a coating process. This is how it is done often. These are just a couple of the different processes. You can actually spray the material on the part, whether it is small part or a very gigantic part like this. You can spray it on there and for various different purposes. But there can be very high-tech applications of coating. And to mention one, if you're looking at hypersonic vehicles, hypersonic means they're at very high speed. The speed is many times the speed of sound that the vehicles go in. And when a hypersonic vehicle enters the Earth's atmosphere, or when it leaves the Earth's atmosphere, because of the friction, there is a very large amount of heat that is generated by friction on the surface. It is shown in red here. And that type of heat generated, which causes high temperature, there are not too many materials out there which can easily withstand that. So they try many different ways of doing that. In fact, they've tried sacrificial tiles. So the coating itself, they purposely let it burn and go away so that inside of the vehicle is not affected. Okay, and so this is very high, advanced level thing. So one of the problems with that is that first of all, the surface is made of some kind of a refractory material. Refractory material is something that withstands high temperature. A typical refractory material is a ceramic, let's say. So if outside is ceramic or titanium, like high temperature material, you want to still try to cool it down. You want to take away the heat as the heat is generated. So you want to put in their cooling channels, small micro cooling channels. I'm talking about a millimeter or smaller diameter cooling channels, and you circulate in the cooling channels some kind of a very cold fluid. Often it is as cold as some kind of a liquid hydrogen or oxygen, that is circulated through, and it is kept cold. One problem we were looking at was, let us say this is the edge, front edge of the vehicle. This is going in supersonic speed in atmosphere. So because of air friction, there's very large amount of heat that is generated there. Now outside is ceramic, some sort of ceramic. These are the tubes. The tubes don't have to be circular, they can be any shape. So this is the tube. Inside the tube we send some kind of a cryogenic liquid. Now the problem is, and there are multiple problems, at very high temperature ceramic will start, let's say we make a tube of some material, some rhenium, titanium, whatever metal. The ceramic starts dissolving literally into the tube. At the same time, the inside fluid starts corroding the tube surface. So typically what you want is something that will keep the dissolving of ceramic away. It is called diffusion barrier layer, DBL. So the diffusion of ceramic or any material should be stopped. On the other hand, inside you want it to be resistant to corrosion for whatever. I mean, for the Mars mission they were talking about lithium fluid, and these are very extremely advanced kind of type of applications. This is Mars mission. When they're going to send somebody to Mars, it is going to take several months to go there and several months to come back, and you should have something going on all the time. And so and of course there are different problems. The space temperature is very low. It is 2 degrees Kelvin. The inside temperature is 300 degrees Kelvin. So it's a reverse problem. In any case, you need something that is protected in terms of heat and corrosion and diffusion and all these problems. And for that, what you need is a tube of certain material, but you need different types of layers on that, because one material is good for corrosion inside, the other one is good for diffusion of something, the other layer is good for heat resistance, and so on. So there are different layers of tubes, and that is done by coating. Problem with coating is that if you look at the coating, now this one probably has some kind of a laminate on the top, right? This table, it's a coating. But when you look at this type of application where the temperature goes up and down, you can imagine it will change the shape slightly and the coating will flake out. It will get released because of the stresses when it goes, when it expands and contracts. So how do you take care of that problem? So let's say you want to make a tube with all the coating in such a way that the coating doesn't come loose. Well, one way to do that is you don't have an actual layer of something, but you have a layer which is already diffused inside. One way to do this is, let's say I have two tubes of 2 layers. So this is what actually we were doing. So this is a molybdenum material, and there is a diffusion barrier layer, the different material A, material B, and we want to create a bond between the two. If you make a simple bond, when it expands and contracts, it will fall apart. So one way to do that is, in here you actually purposely diffuse the material continuously, so that the concentration of, say, this goes from 100% to 0% at this point, concentration of this goes from 100% to 0% at this point, and it is kind of slowly diffused into each other. So there is no single interface. It's kind of a diffused interface. And yesterday for lunch, I was looking at it. There was dhokla, right? And there was this white dhokla there with nice green line in between. But this green line kind of faded on both sides. It is a continuously diffused, nice bonding. So you couldn't separate it clear. So, but this, you want to make dhokla like this, but that will withstand very high temperature. This is the type of coating you want to make. And then you want to make multiple layers of this. And typically, this is material 1, material 2, material 3, material 4. Each one is diffused into each other. Now, how do you do that? And these are typically very high temperature materials. I mean, steel and all that will not withstand there at all. These are, you're talking about 3000 degrees, 2000 degree, 3000 degrees C, which is very high temperature. Pretty much no other material here will withstand that. And this is the actual problem. This is the ceramic layer, and so to stop from, this is the cooling tube, and you have different materials which are diffusing into each other, and you make a coating out of it. So one way to do this is what is called physical vapor deposition. What you do in here is you have something called you have a target, which target means the material that you want to coat it with. So if this is the object and I want to coat this with some other material, then I take a rod of that material. Say this is titanium material and this is molybdenum, this is different. So I, using an electron gun and magnets, you heat this so much to thousands of degrees, it melts, it boils, it evaporates, and a vapor goes out, and a vapor deposits on the surface. So this is kept here, this is the target, and you vaporize it, and it goes on there. And in reality, actually, this is what a typical electron beam physical vapor deposition process looks like. This is the electron gun, and there's a rod, and it evaporates the material, and it goes, it's a vacuum chamber, and it deposits on something there, and it goes there. That's the way typically it is done. Now, if you want to go a little more advanced, this is the facility in our university, Penn State, Pennsylvania State University, and it looks, well, from outside it looks like this. This is a chair, so you can get some idea of what size it is. It's about 1 meter by 1 meter, you can say. Okay, chamber. The chamber looks like this. At the bottom, there are 3 rods, each of about 50 millimeter diameter, and they're made of different materials that you want to do coating from. And imagine there is a part here. So let's say you make a tube here. Actually, what we do is, what we have done is, we took a very thin carbon lead, that like pencil lead type of rod. So literally you take it from the pencil inside rod here. Then you start evaporating A by putting electron gun there, and this is very high power. Each electron gun here is 45 kilowatt. So you can imagine it's a huge amount of power, and you melt it, you evaporate it, and in this little carbon pencil lead, this is spinning and keeps on evaporating on that one. So it makes a layer of A, and then after a while you slightly start slowing down A evaporation, but simultaneously start B evaporation. So B starts evaporating, A is also evaporating, so mixed material is going there, but A is slowly shut down and B is slowly brought up, so that A and B get mixed in together, and a layer of B starts developing on the tube. So if this is a tube, then this is the pencil lead here. First A goes on there, then A goes on slowing down, but B comes in, and then B starts growing, and then you stop B, and then you start C. Again, same way, it is a diffusion layer, it is not a distinct layer. So you don't really I mean, there's no question of this coming apart because it's not a simple layer. The idea is when you're done with that, we take the tube and we bake it at a very high temperature so that the carbon inside gets evaporated and goes out. So what remains is a nice tube with A inside, then B on top of it, and then C on top of it. And we can choose whatever materials that we want, all kinds of molybdenum, rhenium, titanium, or even hafnium, carbide, whatever. So that is a basic process. And so this is the chamber, and it kind of goes on for several hours, or for a day even, and it builds up a tube from there, and it can be used in space applications or whatever. So this is a schematic of the same diagram. Those are the A, B, C rods there. This is where the substrate is, and you can go on spinning if you want even distribution of coating on there. These are electron guns. That's how it works. We want to now mathematically model the process. Then how does it work, or this coating? Imagine I have a surface like this, kind of a long surface, maybe like this. At the bottom, I evaporate, and this evaporated stuff is depositing on the surface. What you can expect is that exactly above the rod, there will be maximum deposition. If this is a surface, this is a plate like this, and as you go away, there will be less and less and less, right, at the further end. So if you take a cross section of the plate after you deposit it, the actual deposit will look like this. It will be thick in the middle, then thinner, 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 and it will go to zero. You go to zero on both sides. And you want to know how will be the distribution exactly. And the reason you want to know is that, first of all, each run takes place for many hours, maybe a day. It is very expensive to set up the whole project. So each tube that we make on that one, about a 6-inch long tube, it can cost a few $1,000s. Okay. So I mean, it is a nice process. But if you can predict how it will be distributed, how much it is, how much is A, how much is B, it will be much nicer, because then you can first you can run the model and find out if it's working fine, and then you set it up, and then you put everything together. Okay. So how do you do the mathematical model there? So for a simple model looks like this. This is the plate, and this is where it is coming from, and it goes on depositing here, and it is thick here and thin here on both sides. And a simple models, you can say that the amount of deposition J that takes place on here in terms of grams per centimeter square per second, per unit time, per minute, per hour, whatever. So amount deposited per unit area per unit time, J, is given by some basic flow rate times cosine to the power n theta, where theta is the angle which is measured from the center as you go away from here. So this is angle theta. When theta equal to 0, when the angle is 0, it is right in the center. When the angle increases, it goes like that. Cosine 0 is how much? 1, right? So at angle 0, it is J is equal to J0. So it is the rate at the center thickness. When angle goes on increasing, just let's forget about n for the second. The cosine theta will go on decreasing, right? It becomes a fraction. And so if this is 1 unit fraction, or if it is normalized with this one, then it will go on decreasing like this, and decreasing like this, and so on. And if you put to the power n, then it becomes of different shapes, so that if n is 2 or 3 or 8, if it is, then it will go very quickly down or very slowly down. And that is one way of modeling the process. This is how the mathematical model was made. That was a long time ago, 1973. But then you're not happy with a simple model. You want to know more exactly what will happen, and if you move things and so on. If you move the substrate, if you rotate it, if it's of different shape, If it is not just like that, if it's a tube, then what happens? And so on. You want to go with different types of models. So in order to model this, now we want to know first of all, how does it flow? The target or the source here up to the plate, what exactly happens to the material? And if you were to look at it from a very closely, from a highly magnified point of view, what you will notice is that just above this target, when you boil it, a vapor cloud comes out. It is boiling, it comes out, and it is a kind of continuous vapor, but outside is vacuum, remember. So it's the molecule starts going apart. Initially they are very crowded. Here there is extremely crowded. So you know what is continuum fluid mechanics versus discrete, where continuum means that air in this room, we can just imagine it is there are of course oxygen and nitrogen and CO2 and H2O and argon and whatever molecules there jumping around, but for all practical purposes it is continuous. You take the smallest size of air that you can see on the top of a little pin, and still it has billions and billions of molecules that you'd say, okay, I'm going to forget about the molecules, I'm just going to call it a continuous region. This is the region where we apply our normal fluid mechanics. The computational fluid mechanics, CFD, is applicable to this region. Okay, and you must have seen pretty much everywhere in our undergraduate course. How many of you are mechanical engineers? Is there any mechanical? How many are industrial engineers? So, how many of you have taken fluid mechanics you must have learned fluid mechanics. So you all learned. Okay. So you know what, I mean, I don't know at what level you are, but if it's postgraduate, everyone has done it. So this fluid mechanics is always, so far at undergraduate level and for most postgraduate level, we talk about this region, CFD region. You cannot assume it's continuous because the molecules are jumping around here, and when they go far away outside, then they just keep on traveling where they're going, and they go in space, go in vacuum everywhere. So how should one do a mathematical model of this? I mean, as it is, CFD modeling is not easy, but then you're getting into this other stuff, right? So this model is going to involve a lot of physics, because you're going on atomic scale or molecular scale or particle scale. So what we are going to, the objective of this work, our work was, this is my PhD student's work, was that first of all, find out what different types of regions that are there, and then you apply different models. This is a computational fluid dynamics model, but when the molecules separate out, you cannot use those Navier-Stokes equations that you may be familiar with. So you use something called direct simulation Monte Carlo technique. So that is DSMC, direct simulation Monte Carlo. Goes into particles, and you look at the particles clusters and how do the particles collide with each other, and after they collide, what happens? Sometimes they agglomerate into blobs, sometimes they collide and go apart, and whatever, So you have to include many different models in that. And then we are going to parametric analysis. And then finally, actually, we are going to make hybrid CFD and DSMC model. And by hybrid model, what I mean is that we will model this, and we will model this, and we will model this in a single mathematical model with a seamless interregime surface, okay, which has not been done before. So that was my student's main, thesis problem. It's an extremely difficult problem. It is highly mathematical problem. I will show you in a minute. You don't have to know the mathematics at this point. We looked at what is done. So CFD is done before. You can do CFD, computational fluid dynamics, for the whole chamber and try to find out where they go and so on. But computational fluid dynamics model does not apply. You remember, we started with a very simple model, and that was this type, cosine model. That's a basic model. That's not even computational or fluid dynamics model. It's just a kind of simple geometric model. And then you go with CFD model for the whole chamber, and there are all little kinds of references. This is very small type, but it's not meant for, if somebody is really interested, we can show that. But this is in computational fluid mechanics model. You can do whichever you want. You can use packages like ANSYS or OpenFOAM, or there are many packages there. You can do that. But what you soon find out is that a region this complicated, there is no computational model or whatever, a ready-made package will do the job. One has to write, different parts of it which are applicable for this. So this vapor transport that happens in physical vapor deposition, we want to characterize it first, see how it works. It will be nice to look at what is called the Knudsen number. Postgraduate fluid mechanics, only you're likely to know, otherwise not. What Knudsen number is about is that if you look at the different particles or molecules, oxygen, nitrogen in air, which are going around and they're hitting each other, and their motion, do you know what is it called? That random motion of particles when they hit each other. It's called Brownian motion. Right? The particles go around in Brownian motion. It is like if you have 10 tennis players here and they are hitting the ball on the wall, different balls on the wall, in different directions. What you will see is that these tennis balls are going around everywhere. Once in a while the balls will hit each other. But most of the times they will probably skip each other, because if there are 10 balls in this room, it's very, very unlikely that they will hit each other. If you go on increasing the number of players, number of tennis balls that are going around in this room, they're more likely to hit each other. So if you make 100 balls, yeah, there is maybe once in a while they will hit you. After all, the ball is of fairly small volume, and it has to travel certain distance to hit the other ball. So if you think of this situation where there are 100 balls and once in a while they hit each other, how much distance on the average a ball has to travel so that it will hit some other ball? That distance divided by the size of this room, for example, the length of this room is L. This lambda over L, normally what happens is Knudsen number. Normally what happens is that the distance is very small, and I am talking about of a very small distances, in less than a billionth of a meter type of distances, a billionth of a millimeter for that matter. And so that billionth of millimeter divided by size of this room is almost zero. Knudsen number is practically zero for normal flow situations, whether it is water flow or air flow or whatever. But when you're talking about situation in our case, where the molecules are going everywhere and expanding rapidly, in a rapidly expanding space, it is not close to zero. Then this distance becomes larger. This distance starts becoming larger before they hit each other, and it becomes comparable to 1. Maybe it is 0.1. Even if it is 0.1, it still is, Knudsen number is pretty high, because it's, if a ball goes and hits another ball in this distance, well, there are too many balls in this room. And so this Knudsen number is what controls the fact that whether you are going to use normal fluid mechanics, that is continuum fluid mechanics, versus discrete fluid mechanics. Discrete fluid mechanics is when this becomes comparable to this. Otherwise this is very, very small, and that becomes different fluid mechanics. So that defines the two regions. When you go on decreasing, let's say you take air in this room and you put a vacuum in there and evacuate the room, start evacuating the room. Normally the pressure in this room in terms of torr, does anyone know what is torr and how much is the pressure in terms of torr in the room? How much is it? It's about 760 torrs. 1 torr is 1 millimeter of mercury, and 76 centimeters of mercury is a normal atmospheric pressure, plus or minus. So 1 torr is the atmospheric pressure. Sorry, 760 torrs is atmospheric pressure. And so you go below that and you go to 10 to the power minus 3 torr, which is very high vacuum. At that time, what happens is that these molecules go around and they don't even hit with each other. They keep on going. Sometimes it starts here, it hits the wall and it comes back. It doesn't hit any other molecule in between because it is very rarefied. The whole gas is very highly rarefied. So as the pressure goes on decreasing, your Knudsen number goes on increasing. And so, like I said, around 1, the lambda divided by L, lambda is the distance that it travels before it hits the next ball, becomes comparable to the distance of this room, maybe height or something. So around 1, it is a different region. So for low Knudsen number, it is called continuum. For very high Knudsen number, there just molecules are going around as if it is open space. In between, it is the Monte Carlo region. That is where the Monte Carlo technique or equations apply. You cannot use your normal fluid mechanics equations like Navier-Stokes equations or whatever. And so this region is a kind of very difficult region around Knudsen number equal to 1, maybe plus 10 to the minus 2. This region is very difficult to solve because you have to actually look at what the particles are going to hit and how fast they're going to hit and so on. When it is very high Knudsen number, 100 means the particle has to go 100 times this distance to hit some other particle. So the probability of hitting is very small. What it means is that if I have a material and I evaporate that, a molecule starts from here, it will go in straight line and it will get deposited there, wherever it ends in straight line. And that is actually very easy. High Knudsen number is easy, low Knudsen number is Navier-Stokes equations, which have been done in, a lot in the literature. This middle region is very difficult. It's Monte Carlo. It is, if you try to do it numerically, it is extremely numerically intensive, much more so than Navier-Stokes and so on. So our problem lies kind of here also and here also. In order to do this, solve any fluid mechanics problem or a problem of vapor and so on, you need to know the properties of vapor. Just like for air, we have equation of state for air, PV equal to nRT or some such equation. And we put the equation, we put the numbers and we do that. And PV equal to nRT is an ideal gas, remember? But if it is not ideal gas, we say PV equal to ZRT, where Z is called, what is the name of that factor? It is compressibility factor. When the compressibility factor is 1, it is ideal gas. That is the constitutive or equation of state. If you say PV equal to ZRT, and if you say that at a temperature of say 3000 degrees, where we operate at around 3000 degrees temperature. Remember, ideal gas works better if the temperature is high, right? High compared to the critical temperature, or pressure is low. But here, kind of funny things happen here. At around here, Z is equal to 0.1 or something, which is pretty far from ideal gas behavior, but still it is not that far. At the temperatures that we are looking at when deposition occurs and all that, at this temperature here, we can get Z, which is 1,000,000 times away from ideal gas behavior. So the gas does not behave like ideal gas, it behaves very differently. And how does it behave? Well, one has to have the properties. Where do you get the properties? Well, you hope that you will get it from research material, but not everyone measures property of every material at every temperature and every pressure range. So somehow, we had to try to get those properties. We did that for, we tried to calculate Z and looked at different ways of making an equation for Z, Z being that compressibility factor. And once you calculate what is Z, then you can calculate the properties of the substance. But that is how it worked. And depending on how far it is from, how far away it is, well, what is the value of Z, the compressibility factor, or more than that, I won't make it complicated unnecessarily. But when it is rarefied, you can imagine, does anyone know what is a Mach number? You know what's a Mach number, right? Mach number is how many times the speed is compared to sonic speed. Speed of sound. So speed of sound normally is somewhere around I don't know, 300 some meters per second. Mach number 2 is double that speed and so on. You know, some fighter jets go at Mach number 2 or 3 or 4, which is 4 is pushing too much. Right. And normal jets go just below 1 Mach number, so they're subsonic. Most of the commercial transport or the jet transport or everything, I mean, normal transport is subsonic. Now the real definition of Mach number is a thermodynamic definition. Doesn't even know what is the definition of Mach number. In terms of temperature, is Mach number is equal to square root of gamma RT, exactly, where T is the temperature, R is the gas constant, and gamma is the specific heat ratio, right? And now remember, if the temperature is very low or very different or very high, the Mach number can be very different. And in rarefied flows, the Mach number definition changes quite a bit. In fact, our Mach number calculation, the Mach number goes to 10,000 almost, 9,000, which is very unrealistic behavior of material. In fact, Mach number definition does not really apply in that region, because if you look at the standard, the thermodynamics that you learn is called classical thermodynamics. It is all based on continuum. That is, you don't have particles going around. When you go to quantum mechanics or discrete mechanics, there is no such thing as temperature. There is just the kinetic energy of molecules. And I don't know if you have learned the statistical thermodynamics. If you take a course or subject on statistical thermodynamics, you will know that there is no such thing as temperature at that level. You just talk about kinetic energy and other energies, potential energy and so on. So Mach number is really, not a realistic way of looking at it, but that is where you start. And so when we started this, we were really puzzled as to what to do in terms of writing the equations and putting the equations together, because it was not just continuum mechanics here, but it was all kind of more like quantum thing, particles going around and so on. We did many attempts at it. This figure kind of nicely summarizes what are the different regions that you're looking at. This is that Knudsen number, it's a saturated Knudsen number. They've defined in a certain way. This is the pressure. And what it is saying is that there is continuum region when it is low Knudsen number, and then there is a free molecular region. That means the molecules just go freely, they don't even collide with each other. Before that, this transitional region where they collide quite a bit. Then there is a slip continuum region where you might remember in fluid mechanics, when there is flow going over a solid object, such as this object, if I were to blow, or if fan is blowing air on this surface, the boundary condition at the surface is, what is the speed? Speed is equal to 0. That is, speed is actually same as the solid speed, which is 0 in this particular case. The reason it is 0 is because it is a no slip condition, if you remember from fluid mechanics. Well, when you go to molecules, a particle level, it is not exactly 0, because the particles may just skip, just hit and come out. And so the speed is not 0, exactly, speed of, it continues, and there is a slip continuum region. So when it is rarefied, when it's low density region, there is some speed that can occur even at the solid boundary, which is another complication. And then of course, when it is transitional, then it becomes very complicated, in the sense that what we are studying is that when the molecule of this one material that is going, and if it hits the substrate, usually it will get deposited. It won't even get reflected, but sometimes it may, or so on. So we had to somehow model the whole thing. Basically, my student, poor Kevin, he was working on this for many years, pulling his hair how to do this, and we are going back and forth, and because it is not there in any of the books, it is his own PhD thesis. And so for titanium, we got all the equation of state and everything, because we're looking at titanium vapor. Titanium is very high temperature. So this is computational fluid dynamics and direct simulation Monte Carlo solver. For basic equations, we used a program called OpenFOAM. Does anyone know what is OpenFOAM? Has anybody used OpenFOAM? If you haven't, I would highly recommend you to do that, because first of all, it costs nothing to use it. And it is probably the most powerful fluid mechanics type of program that is there. I would say it is more than, personally I like it better than Fluent or other programs which cost $50,000 sometimes per year to lease them or to rent them. OpenFOAM is open source code. So you can get open source code and you can change the code the way you want. And you can add things. So we wanted to add, it's not just fluid mechanics, we want to add the Monte Carlo simulation in that and so on. So this is the basic equations, the CFD equations, these are kind of well known, Navier-Stokes equations and all that. The continuity equation, mass conservation, momentum conservation equation, Navier-Stokes equation, these are all vectors, so they are x, y, z, 3 directions. And then there's the energy equation, and then constitutive equation is the equation of the state for the gas, or the way the properties are connected. And there's heat flux equation. So there's a basic set for fluid mechanics. This is well known, this is well programmed into the system. For direct simulation Monte Carlo system, where we have now particles which are going around, you cannot use a continuum equation, you use the so-called Boltzmann equation from physics. And so in this equation, what you do is, you have a probability density function f, which says that the probability of having f, density of f, depends on the time x, y, and z, the space coordinates, the time coordinates, and also the speed. That is, the probability of finding a molecule between t plus delta t and x plus delta x, y plus delta y, z plus delta z, and speed of v plus v and v plus delta v is so much. And then you integrate it over space and so on, and find out how it is. That's called Boltzmann equation. It's a very well known equation. You can go back there and solve it. And then there's a way to go back and forth. I won't go into that very much, but I guess the main thing is that how do you take the particles and how do you make sure when they collide with each other? The collision can be of different types. Either the particles, when they collide, they can make a bigger particle, they get together, or they may collide and go away, or something in between that can happen. Same thing happens when they collide with the surface, where they get absorbed or they don't get absorbed. So there are, in the past, people used a certain way. Now remember in that figure where we have continuum mechanics and then there is direct simulation Monte Carlo or particle regime. In between there is an interface, and how do you handle the interface mathematically, right? From equation point of view. So people have come up with certain ways of ghost cells and so on. So my student came up with a very interesting technique actually, and then the idea was that how do you patch different regimes, and let me go here. Okay. So this is CFD region, no problem, you can calculate it. This is a DSMC region, you can do it. But what happens at the interface? On one side there is continuum mechanics, the other side there is not. And where it meets, and how do you define that? How do you find out? Because it's not given. You have to mathematically find it. And so what kind of boundary condition you will use, and that was the biggest headache in the whole. So basically we came up with, and I had to credit my student, he did a good job in that, how he matched the density and the particles and went on checking whether the boundary, what is the boundary. On one side of the boundary there is CFD formulation of equations, on the other side of boundary there is direct simulation Monte Carlo technique, and you go on defining the boundary. Basically that is how he calculated that. It becomes highly numerically intensive, and then this is the overall flow chart that you initialize that, and then you go do the CFD calculation, and then you go into DSMC region and you do the calculation and you check whether it is still continuum region or not. If it is continuum region, you go do CFD and you keep on doing. If it is not continuum region, you call it direct simulation, then you stop there and define a boundary there, and you go on defining the problem from there. And then finally we have some comparisons. So what we did was, going back to our coating problem. If you do only CFD calculation, what results will you get? If you do only DSMC for the whole thing, what results you will get? And then if you go hybrid, that means part CFD and part DSMC, which was not done before with the right kind of boundary, which is, this is the first time we have, Kevin and us, we have done it before. So if you just do this, and if you have different parameters, and if you vary the different parameters, you find that in which parameter range the fluid mechanics works, which parameter range DSMC works, and then how do you patch it, which way hybrid works. And that he did, the parametric study, which is, each run would take days, by the way. I mean, a simple run would, and that is not on a small machine, on a cluster of some 256 computers connected together. And it's a kind of major kind of thing. So I have the CFD studies. I shouldn't flip the slides quickly, but this is computational fluid dynamics study, and then for different boundaries and pressure gradients and all that, we tried that for the whole region. Then for DSMC, we tried for the whole region, and then we looked at hybrid for the whole region, where part of it is CFD, part of it is DSMC, and the boundary is automatically calculated by the program, which was a very, very interesting thing. That by itself, the program keeps on working back and forth and decides, okay, this is where the boundary is, and it works. And then we did some comparison. First of all, we had to do validation. As I said, a lot of slides I borrowed from my students' PhD defense. We went over this many times, and so you have to, when you do a computer program, the biggest problem with any computer program is that if you put an input, it will give you an output. It could be total garbage, but it will give you an output. Then you decide, okay, well, is this reasonable or is correct or not? How do you know that? So you go on doing different checks. One is that you try it with a known solution, or you can also do the mesh independence. That is, you increase the mesh size, and see whether it is independent of mesh, because the result should be independent of what assumptions you make there in terms of mesh. So we did different kind of validation studies for different geometries for known results, and basically when it checked, we went ahead. When the thing compared, we went ahead. This is for computational fluid dynamics, flow field, and for different parameters. I'm not going to go over this. This is the DSMC I was saying. DSMC is the particles. So what you have is the particles going around all over. It is not continuum mechanics. It is what we had to do, or what Kevin had to do there in this, is that he had to model how the collisions took place and what kind of collisions, and that was programmed in fully, and that was added to the open foam. Basically this software package goes on growing, and you finally compare. I will kind of quickly go different hybrid shapes to begin with. I will just, and then we compared this results with experimental data we got from somewhere. This Mukherjee and some other paper, they had done this, and based on all that, and so they had a different material, copper. So you have to get copper data and copper everything, and then study that, and there is geometry is different. But I will just jump to, we did it with all three hybrid. Computational fluid dynamics, DSMC, and hybrid, the two together, two separately and one combined. That we develop an improved physical vapor deposition material model, and the results, for rapidly rarefied flow. That means the flow is dense at the source, but goes on rarefying. It becomes sparse, and under certain circumstances, after we created the hybrid solver using base computer, base software package of OpenFOAM, although all the hybrid stuff is including the computer software that we added to the OpenFOAM, and there are certain regions that basically this is important. A hybrid CFD DSMC solver displays certain virtual source characteristics. That is, if we have if this is a chamber and if it is the source where the material is coming from, it is as if there is an imaginary source somewhere above that where mass is coming from and is going in all directions, and then what will happen is what it looks like using this, and you can prove this. Going back to the application, so why do we do this mathematical model? Why do we go through all this trouble? Because with mathematical model we can basically do all the experiments at our desk using a computer. We go through all these different scenarios and then we find out, well, this experimental way looks like what comes closest to what we want. Because each run may end up costing you $1 million to do everything and test it and so on. So instead of doing $1 million run every time, you do modeling and then you pick the optimal conditions and then you do the runs after that. So my email ID actually is an extremely easy email ID. It has only total 11 characters, but my initials AKK, Anil K. Kulkarni, Armenian, AKK @ PSU for Pennsylvania State University .edu for education. So akk@psu.edu. Feel free to send me an email. When you send me an email, in the subject field, write that you're from whatever we met at GTU or something, because every day I get 100 emails from students all over the world. Well, thank you very much. It's all done. Thank you.